Welcome to the Explainer. Today, we're taking that totally intimidating prerequisites coding problem and, well, turning it into a fun, intuitive whiteboard puzzle. If you've ever just stared at a massive, tangled web of course requirements and thought, where do I even begin? You're absolutely in the right place. So here's our agenda for today. We're going to cover 1, the prerequisite problem, 2, spotting the cycle, 3, the in-degree concept, 4, Kahn's algorithm in action, and finally 5, complexity analysis. Let's get right into it. Section 1, the prerequisite problem, scheduling constraints. All right, so the fundamental challenge we're tackling here is this. Can you clear all your classes without getting stuck in an infinite loop? In this classic coding problem, we're handed an integer n. That's the total number of courses you've got to take, numbered from 0 all the way to n-1. And along with that, we get an array of prerequisite pairs. Essentially, each pair tells us that one specific course has to be knocked out before another. So our job? We need to write an algorithm to figure out if it's actually mathematically possible to enroll in all n courses. Simple enough, right? And this setup brilliantly illustrates the whole crux of the problem. Sometimes course requirements tangle themselves into totally impossible dead ends. Look at how course 0 points directly to course 1. That just means 0 is a prerequisite. Totally fine. But then look at courses 1 and 2. Course 1 requires course 2, but wait, course 2 requires course 1. It's a classic catch-22. You literally can't start either of them. Moving on to section 2, spotting the cycle, the ultimate roadblock. So whether it's a tight, simple 2-course loop like we see on the left, or a wider 3-course loop on the right, this circular relationship, which we call a cycle, makes full enrollment basically mathematically impossible. Listen, if your graph has a cycle, I don't care how big or small it is, you're stuck. There's no way you're graduating. Because of that, our algorithm's main mission isn't just sorting the courses nicely, it's acting as a detective to figure out if one of these fatal cycles is hiding anywhere in our data. Which brings us to section 3, the in-degree concept, counting our locks. Okay, here's the core definition that really makes the magic happen. In-degree is simply the number of directed edges, those arrows, pointing inward to a specific node. I actually really like to think of the in-degree as the number of locks on a course door. So an in-degree of 2, that means you've got 2 prerequisites you need to finish to unlock it. But an in-degree of 0, boom, the door's wide open, entirely unlocked, and we can just walk right in on day 1. Now, by systematically finding and then clearing out these unlocked courses, what we're actually doing is performing a topological sort. This is just sorting graph vertices, so for every directed edge from U to V, node U always comes before node V. In plain English, it reveals the exact step-by-step path to graduation. It's basically the ultimate academic to-do list. All right, now for the really fun part. Section 4, Kahn's algorithm in action, the domino effect. Step 1. We kick things off by tracking the in-degree of each and every course. We literally just increment a counter by 1 every single time a course shows up as a dependent in our prerequisite array. You can see how those orange arrows map directly from the array straight down to our list of locks. Every time a course is on the receiving end of a requirement, its lock count goes up by 1. Moving to step 2. Take a close look at courses 0 and 3 highlighted in green. They have exactly 0 locks. Since they're totally free of prerequisites, we push them right into our processing queue to tackle first. They are without a doubt our perfect starting points. Step 3, time to actually take a class. As we pop course 0 off the front of our queue, we successfully complete it, which immediately drops the lock counts of its dependent courses 1 and 2 by 1. Check out those crossed out numbers on the dependents. Course 1 just went from having 1 lock down to 0 locks. Awesome. And then step 4. This is where the domino effect really kicks in. Because course 1's lock count just dropped to 0, it's completely unlocked. So what do? It jumps straight into our queue. We just rinse and repeat this process. Pop an unlocked course, decrement the locks on its neighbors, and the second a neighbor hits 0, throw it right into the queue. But hang on. What happens if our trusty detective tool runs into a villainous cycle hidden deep down inside a much larger graph? Notice here how courses 0 and 3 are unlocked and ready to go, but if you follow the arrows between courses 2, 4, and 5, yikes. They form a completely hidden closed loop. Watch exactly what happens to our algorithm here. We process the unlocked courses perfectly fine. 0, 3, and 1 are done. But then suddenly, the queue just empties out entirely. Why? Because absolutely none of the remaining courses can reach an in-degree of 0. courses 2, 4, and 5 are permanently locked, just endlessly waiting on one another. We literally can't push a single one of them into the queue. So here is the absolute crucial takeaway. If the queue empties before all N courses process, a cycle is found. If we finish processing and we haven't hit all N courses, that cycle exists and graduation is completely off the table. In practice, we just keep a super simple counter of how many courses we actually popped from the queue. If that counter does not equal our total number of courses at the end, bingo, we've caught a cycle.
All right, Section 5, Complexity Analysis, Evaluating our Solution.
So because we iterate through every single course and prerequisite edge exactly one time, both our time and space complexity sit perfectly at big O of n plus e. Setting up our adjacency list and those lock counters takes time proportional to the number of edges. And processing the queue just means we look at every course once and follow each edge exactly once to decrement the locks. The memory footprint, similarly lean, tied directly to storing the graph in our simple tracking arrays. Honestly, it's just an incredibly optimized, elegant way to solve this whole problem.
Before we wrap up this explainer, I really want you to ponder this. Beyond just scheduling your academic classes, where else in our digital lives does topological sorting govern the sequence of events? Well, think about software build systems. When you compile a massive software project, certain code libraries absolutely have to be built before others. Kahn's algorithm is the exact same logic that package managers and build systems use under the hood to calculate that perfect compilation order without getting stuck in dependency hell. So hey, the next time you're installing a software package, just picture those dominoes falling and all those locks opening up. Keep learning, keep building, and we'll see you on the next explainer.